Awesome. Welcome to the video. This video is going to be about histone modifications, which is a way we can epigenetically modify and change the level of gene expression associated with DNA and further on mRNA. So there's going to be two heavy hitters in this concept. The first is going to be acetylation. The second is going to be deacetylation. So what is acetylation? Acetylation is a process of adding acetyl groups, so COCH3 to chromatin. This will further increase transcription. But why is this occurring? So when we have our acetyl groups being introduced to our histones and chromatin, they're binding in a manner that is going to space out our histones and chromatin. This is going to allow our transcriptional factors, such as TF2D, it's going to come in and it's going to be able to bind with that DNA. That further binding with those transcriptional factors is going to allow our heavy hitter RNA polymerase 2 to come in. RNA polymerase 2 is going to elongate and to produce our mRNA in a 5' to 3' directionality. So acetylation, spreading out our histones and chromatin, it's allowing those transcriptional factors to bind in that DNA, and it's producing a euchromatic state. So it's going to be a loose chromatin. Deacetylation is the opposite effect of acetylation. So you're removing those acetyl groups. So you're deacetylizing, and so you're eliminating the spacing that we've created. And therefore, we're decreasing transcription because we're inducing a more heterochromatic state, a more tightly bound state. So imagine you're a transcription factor and you're trying to bind to this DNA. It's going to be blocked off by this deacetylation effect. But another way we're going to influence chromatin and histones is something called methylation. So what is methylation? So methyl group is going to be CH3. These are going to be introduced to the histones and chromatin. An increase in methylation is going to yield a decrease in transcription, but a decrease in methylation will yield an increase in transcription because our DNA is going to be more accessible to transcriptional factors. And what happens when we have those transcriptional factors, such as TF2D? Those transcriptional factors are going to promote the attraction to RNA polymerase. So this RNA polymerase is going to come in, it's going to be attracted to the transcriptional factors, and bang, it's going to start producing that mRNA segment in that 5' to 3' directionality, right? So methyl groups are making things tighter. And then if you're decreasing the level of methylation, we're making things looser. So it's kind of the antithesis to acetylation. So the key idea is an increase in acetylation will space out our histones. This will allow for optimal transcription. But on the flip side, if we're increasing methylation, we're making the DNA less accessible to transcriptional factors and RNA polymerase. We're making it too tight, and we're making it more heterochromatic. So here we have an image detailing this methylation. So we have our CH3 coming in, our methyl group, it's binding to our histone, and then it's creating this heterochromatic environment where the transcriptional factors are unable to bind to our histones and unable to attract RNA polymerase. So transcription is impaired. Well, I hope you guys enjoyed the video, and thank you.